Hello and welcome to this presentation on the progress from our collaboration on MicroED with our partners at JEOL. My name is Fraser White and I'm the Product Marketing Manager for Rigaku Oxford Diffraction's single crystal diffraction products. Today we have some exciting news for you, but let's take a moment to go back 1 year. So on the 25th of May 2020, Rigaku and JEOL were both seeing the potential held in MicroED for the crystallographic community. And with the strengths of Rigaku in single crystal diffraction and the strengths of JEOL in electron microscopy, we formed a collaboration to explore new products for the MicroED community. Together over the last year, we've been working towards this goal, and I'm very pleased to say that we have something very nice to show you today. Now, some of you may not be so familiar with MicroED, and in fact, the cutting edge of X-ray diffraction for that matter. So let's take a moment to recap on what's possible with each. So our current lineup of X-ray equipment allows you to study a wide range of sample sizes. The CrystalLab Mini over here on the left is a fine focus instrument, and if you were looking for a good sample size to match it, you'd be looking at something like this on the order of 300 microns across. That's not to say that it can't study bigger or smaller crystals. At the opposite end of the scale, we have the CrystalLab Synergy Custom with the FRX source. With this system, we're pushing the boundaries of single crystal X-ray crystallography, and with it we can study samples as small as 1 micron in the smallest dimension. This picture here is a crystal which is 3 by 2 by 1 microns, from which we have been able to solve the structure with an FRX. However, this is right at the limit not only of what we can measure today, but also what we can practically see and mount on the system. So what if we wanted to study smaller samples than this? Well, this is where MicroED can help us out. MicroED sits on the other side of this 1 micron barrier that I've drawn in here, for reasons I'll cover in a few slides. So just to give you a brief idea of the scales we're talking about here, if we use the tallest building in the world, which is currently the Burj Khalifa, to represent a sample we'd use for the CrystalLab Mini, what kind of size building would we need to represent our FRX instrument? So it's something a bit smaller than a typical house. And to represent that, I found this very proud homeowner sitting in his luxurious home. So how about our MicroED sample? Well, here is a slightly less luxurious doghouse, but the owner looks quite happy in there nonetheless. So MicroED presents us with some challenges. Electrons interact very strongly with matter, and this imposes an upper limit on the size of the samples that we can study for a couple of reasons. The first is that it only typically takes a very small crystal to act as a beam stop and completely stop the beam. And you can see this when you're visualizing the samples. So in this image down here, you can see very dark means that the electrons are not passing through. So the second is dynamical diffraction, and this is where the electron beam is diffracted multiple times on its path through the crystal. This complicates things dramatically, and the thicker your crystal, the more dynamical effects can cause problems for your structure, solution, and refinement. So that favors a thinner crystal as well. Another issue we face here is sample decay. So unsurprisingly, hitting your crystal with a high power, highly charged beam tends not to be too good for it, and we see significant sample decay. This can be slowed a little with cryocooling, but it's still something that we have to think about and something that happens while we're looking at the samples and running diffraction experiments on them. So lastly, we have to do all of this in a vacuum, and that's because any gas in the path of the electron beam will also absorb and diffract it. So it doesn't take much to stop the beam or to ruin the data. And just to point out on the right here, I have a couple of crystals that are good sizes for electron diffraction experiments. So the smaller is generally better, but this one will still work too because it's quite transparent. So today is a very happy day for us as we're announcing the launch of our new product, the CrystalLab Synergy Ed, which is the world's first commercially available dedicated electron diffractometer for the home lab. So here it is. We'll go into some more details shortly, but I'd like to point out that the CrystalLab Synergy is not a high-resolution TEM. We've worked with JEOL to develop a system specifically designed for electron diffraction. While there is some imaging capability, this is only really to allow sample visualization for selection and centering purposes. The system is also designed to use the rotation method, so it should feel familiar to most X-ray diffractionists out there. Inside the CrystalLab Synergy ED, we have a JEOL 200 kilovolt electron gun, and that's in a vacuum column with beam shaping and focusing optics also from JEOL. And at the other end, we have the Hypix ED, which is a special Hypix family detector optimized for use in electron diffraction. As this is an HPAD detector, the benefits of zero readout noise and zero dark current are built in for high quality data, and we also have zero dead time mode to ensure that there's no signal loss between frames. The sample stage offers XYZ movement and a tilt axis. There's a standard sample holder which can be used for ambient experiments, and there's also a cryo holder if you need to do low temperature experiments, for example to stabilize sensitive samples. The system is built in a vertical arrangement in a compact floor standing cabinet, both for mechanical stability but also so that it will fit nicely into X-ray diffraction labs without any special requirements of an electron microscope. So you can put it alongside your X-ray equipment. So I also want to say that the system is controlled and operated by Chrysus Pro. So for the crystallographic community, you should find using the CrystalLab Synergy quite familiar, but intuitive in the areas where it differs. So there are, of course, a few differences in the experimental setup when using electrons instead of X-rays. As I mentioned before, we have to have the samples in a vacuum so that the electrons can reach them, be diffracted by the sample, and then to reach the detector on the other side. This means that you'll need to consider if your sample will survive in a vacuum in the first place. So materials that are sensitive to solvent loss could be a problem unless you freeze them first and have a cryo sample holder. We also only have a single rotation axis here, which can mean that getting complete data from a single grain will be impossible or difficult for low symmetry. To overcome this, we can merge data from multiple grains to make up a much higher completeness dataset. And we have to view the samples also with the electron imaging. So we need to be aware that that means the sample is being exposed to damaging electrons during sample selection and centering. And I've also already made this point a few times, but the samples have to be small enough that the electron beam can penetrate them, and also to minimize dynamical effects for good quality data. So next I'd like to show you the various stages of an experiment as best I can in presentation form. Unless you have a sample that's already a very fine powder, we typically have to grind the crystallites to get them small enough for successful measurements. So that can be done quite easily by simply grinding some of the sample between two glass slides, like you can see at the top here. And once that's done, we need to get the sample onto a sample grid, which looks like this. You can either do that either by trying to sprinkle some of the sample onto the grid, or you can put the grid into an Eppendorf tube like this, along with some of the freshly ground sample, and then just shake it up together. By doing this, some of the crystallites will stick to the sample grid, and then we can load it onto the sample holder, which is this long cylinder here, ready for insertion into the electron diffractometer. So next we need to insert the sample into the instrument, and my colleague in Japan, Dr. Akihito Yamano, kindly recorded this video for me using our prototype instrument in Japan to show how this is done. So first we have removal of the sample holder, and you can see that he's already pulled out the sample part way. So this is because there is an airlock between the atmosphere and the high vacuum inside the diffractometer column. Once he's pulled it out, we'll show you how to reinsert it. So you can see now that he's putting the sample holder back in. And in a second, he'll switch on the airlock pump to evacuate the airlock. So this takes a few minutes for the vacuum to reach a good low level. And I've shortcutted the video here so that you don't have to sit and watch the whole process. But when the system is ready, you'll see the LED light here will light up, and that tells you that you can then complete insertion of the sample holder into the device. So you'll note that he's turning the sample holder as he goes through. That's to allow it to be inserted through or removed without breaking vacuum. So here's the first look of Chrysus Pro's interface for MicroED. You can see from the image here that we're using the Hypix ED detector with the electrons from the electron source to visualize the sample grid. So the Hypix ED is also used for recording the diffraction data, of course. And as we're using electrons in both cases, we need to make sure that we can keep the dose as low as possible when we're looking for a sample. Chrysus Pro will automatically change the diffractometer settings to try and do this. So there are presets for the visual mode and the diffraction mode, although the user is free to override those if they prefer, but the defaults are designed to minimize the dose as much as possible when it doesn't need to be high. When you're in diffraction mode again, Chrysus Pro will use the appropriate settings to achieve good diffraction, but again the user can change this preset if they wish to. So I'm going to show you now how sample browsing works through the use of a few short videos. So this is the view that you'll get when you're in the visual mode. And from here there are a few ways to navigate. So the first is to simply click on the image where you want to browse to, and that position will be brought under the crosshair. So the crosshairs here show you where the beam is, and they also give you an idea of the scale. So the diameter of this circle here is 4 microns. So as you can see as the video loops, that you just click on the sample that you want to get to the beam, and Chrysalis will bring it to the right position. If you prefer or you need to fine tune, then you also have step movement, so you can use the up, down, left, right buttons and these buttons that are on the outside to make small, medium or large jumps in each direction, and you can also go in diagonal directions as well. There is also a neutral, XY neutral button, which brings the sample stage back to the neutral position, which is kind of like the starting position or the home position if you prefer. It can also be helpful to zoom out from the grid. So if you're looking for samples, sometimes you can zoom out to have a wider overview. or if you want to make a big movement in one step. So you can see from this video loop that we're zooming out, and it gives you an idea of how much range we have. So you can see the sample we were zoomed in on is at the top here. And one thing to note is that the image position does change slightly as you zoom out, but when you zoom back in, it will come back to the same position. The color scale also changes a little, so that's something else that you may need to change if you find that the image becomes overloaded. So you should always center the samples in the standard view, because that way you know where the beam is. So if you need to move even further than that, we also have the Minimap. So this is a low magnification snapshot image of the grid, which you can take at any time. And then that will be stored so that you can easily jump around on the sample grid. We also have markers which you can use to see where you've been on the grid. So these little red dots are the markers. And this will give you an idea of which parts of the grid have been exposed to the electron beam. So if you need to find an area which has not had a high dose yet, then you can use this information to quickly and easily find somewhere and navigate to that part. So this also works on point and click navigation, with the added step that we have a go to selected button here. So once you've clicked on the image on a position that you want to go to, rather than simply moving, you have to then press go to selected. And this is done to prevent accidental clicks from causing you to lose your place, or if you were on a good sample and you click by mistake on the Minimap and lose that sample by mistake. So once you've found a good looking grain, you'll generally want to see if it will diffract. So you can do this in a few ways. The most obvious is to take one diffraction image, which is this button here, and that will allow you to record a still image for a given time period. So you only need to click once, and then you can enter the exposure time you want, and Chrysalis will switch modes and record the image, and then blank or shutter the beam to prevent damage to the sample. If you like what you see, you can then continue to an experiment if you've already centered the sample, or you can return to the visual mode to center it, or if you need to find something else. Another way is just to switch to the diffraction preset, and then you'll see a live image of diffraction from the crystal, though at times the frame rate may be a little too fast for you to properly gauge the diffraction. Centering is a little different to an X-ray diffractometer. We have two ways to do this in Chrysus Pro. So the first is to manually adjust the Z height with the Z plus and Z minus buttons. First you need to tilt the axis, and if the sample moves off the crosshair, then it means that the Z height is wrong and we need to adjust it. So you can see that this is being done in the top video with these buttons here. And the second way to do it, which is easier, is to use the centering mode of the point and click. So all you need to do here is to rotate by some amount, switch to the centering mode, and then you can click on the sample again. Chrysalis will then make the needed calculations and adjust the height to bring the sample back on the rotation axis. And you can see that that's being done in the bottom video. When you have a nice sample and you have it centered, all that remains is to run your diffraction experiment. So you can click on the Diff Exp button from the visual mode, and Chrysalis will switch the diffractometer into diffraction mode and give you the experiment setup GUI. For MicroED, experiments are simple rotations, so you don't really need to give too much information, just the exposure time, the scan width, and the scanning range, along with some information about the sample and a name if you wish. Chrysus Pro also has the concept of sample grids built in, so you can group together the experiments by a sample grid, as they'll typically be grains of the same material. The diffraction experiment then proceeds just like an X-ray experiment. So that means that we have concurrent automatic data processing and even the possibility of AutoChem being run. One difference to X-ray, though, is that due to the limited sample access, we will often need to merge the data from multiple grains to get the completeness up to an acceptable level. So dataset merging is now easier in Chrysus Pro, and there's a GUI which is at the bottom here, which lets you select multiple datasets to merge and output a file for refinalizing to apply all of the corrections and scaling to get the HKL file for structure solution and refinement. Okay, so I wanted to now show you some of the data from the CrystalLab Synergy Ed to show you what can be done. So up until quite recently, I was a complete novice with electron diffraction. And after having a short driving lesson from some of my colleagues in Japan and in Poland, I was able to produce this data. So this was my very first data set, actually, or rather data sets, I should say. So this is 7 data sets merged together, and you can see them at the top here. And these were collected in a batch, so one after the other, with a few exceptions. So there were about 10 grains in the run, and 3 of them turned out not to be good, but the other 7 were quite good, so I merged them together, and this was the result that I was able to get. So I just wanted to, before showing you the final result, show you that even the hydrogens show up nicely in the difference map, so you can see them here. And the ADPs are all very nice. And this is the final structure. So you can see that the FOBS FCalc graph here is very nice. We got quite a low R factor here, and this was refined using electron SFAC instructions. So I did use some omits, and I didn't want to go too crazy with those. It was possible to reduce this number a little bit lower, but I decided to be a bit more conservative for this webinar. So here we are collecting data on a grain. I wanted to show you an experiment running live. So this is the grain we're collecting on. And what I've done here is recorded the experiment from start to finish with a few little speed ups on the way, and I'll indicate in the top corner here when I've speeded it up. So you can see some very nice diffraction coming from this sample grain already, and this is just from the live view. So I've just given the grid a name so that I can remember that this experiment was done by me. And I'm just going to enter the elements rather than the full chemical formula just to help AutoChem. And then I'm accepting the defaults. So I'm scanning from -60 to 50 degrees. And that was because as I rotated to a high positive angle, there was a crystal or maybe the grid, I think, in the way, which blocked the beam. So this is now running at 3 times the speed, just so that we don't have to wait for all of the images. And you can see at this point, I'll just pause it quickly to show you that the rint that we're getting is 8.9%, which is very nice. We'll just carry on for a little second until AutoChem kicks off. So you can still see very nice diffraction coming in. And there you go, you can see AutoChem solving the structure. So I've just paused that again to show you that the R1 at this point is about 20%. And we'll get some more data in as the experiment continues. But you can see it's quite nicely solving with AutoChem. So of course some of the atomic assignments are not entirely correct here. So if we make those changes and also manually process the data to try to get the best possible results, this is the results that we were able to achieve from that sample. So remember, this is a single grain, and we collected from -60 to +50, and from that we managed to get a completeness of 62%. So normally we would then go and find another grain and merge the data together to bump that up, but for the purposes of showing you an experiment from start to finish, I left it as is here. And from the single grain we got an R-int of 7.9% after manual processing, and that brought our R1 down to 15.07%. Again, we're using the electron SVAC instructions here. And you can see that the initial solution and with anisotropic refinement of the main atoms, you can also see the hydrogen atoms showing up again in the Fourier difference map. So adding the hydrogens in and then doing some cycles of refinement, refining the extinction and making some omits for some of the worst offenders. This is the final structure that we got, and this is the appearance of the FOBS versus FCalc graph. And you can see it's very nice. So even for single grains, we can get quite good data and solve and see structures quite nicely. So I just want to thank you all now for attending and listening to me. I wanted to make a few points just before finishing. So the CrystalLab Synergy Ed will be on sale from the 1st of June. So that's about 1 week from now. So I'm sure you're all interested to know the price. And for that, I'm afraid I will have to direct you to your local sales organizations. And lastly, we will have limited demo capacity at first. So at the moment, we only have our prototype in the factory in Japan to run demos on. So if you're interested, we'll do our best to accommodate you, but please be aware that we may be very busy. If you do want a demo, please get in touch with your local sales organization and we can take it from there. So if you need to find out where your local sales organization is or how to get in touch with them, you can do that either via our website or by contacting us with the information shown here. So thank you for listening.